Abhishek mentioned, my name is Timothy Canham, and I am currently the Mars Helicopter Operations Lead. Before that, on Mars Helicopter, I was the software lead, and our team put together the actual software to run and execute the helicopter. And so what I want to talk to you about today, though, is how you actually operate a helicopter on Mars in 3 easy steps. It's sort of a tongue-in-cheek because it was actually a lot of hard work, but it's really paid off. And I do work at the Jet Propulsion Laboratory, which is a NASA center that's run by Caltech. So I'd like to go over these slides, and then, as Abhishek, forgive me if I mispronounced your name, mentioned, we will have some time for questions at the end. So how do you actually operate a helicopter on Mars? Because it's a challenge, because we're here on Earth and Mars is a long ways away. So how do you actually plan for that? And as a cover photo, this is one photo I really like to show. It's the selfie that the rover took. It took several dozen pictures and stitched them together. You can see the robotic arm being extended there so it can get in the rover and the helicopter. This is right after we got deployed to the surface. And so you can see the rover looking at the helicopter and then looking at the camera. So it's kind of a cool picture. You can get almost all of these pictures you can get on the JPL public website. There are some internal ones which I was able to release that will show you some things that we put together as part of our operations, but most of these pictures are accessible through the website. So first of all, you want to ask the question, why is flying on Mars so hard? And the first answer to that is the atmosphere itself. The atmosphere is 1% of the density of Earth's atmosphere. And so we're used to helicopters on Earth being able to fly in the thicker atmosphere of Earth. There's a lot of skepticism, actually, that we could even begin to fly on Earth. So one of the very first things we had to do back, it's been a long time, in 2013 or 2014, was to demonstrate that we actually could fly at all. We had a little demonstrator that was, if you want to put it that way, it was the very first vehicle that we put together that we flew inside of a chamber with a human operator, and it showed us 2 things. Number 1, that you can fly in that kind of density, but number 2, that a human operator can't possibly do it because of the thinness of the atmosphere. It was too hard to control, and it actually ended up bouncing off the wall and wrecking itself. But that gave us the first clue that we could actually fly. So the second part is why it's so hard to fly on Mars is because the temperature. It's really cold at night, and so you have to design the electronics to survive that. You also have to keep the helicopter itself warm, so you have to put in a thermostat circuit of some kind and heaters of some kind. The main part that's vulnerable are the batteries, because if the batteries were able to reach minus 90 C, the actual ambient temperature on Mars, then they would probably freeze, and the helicopter would not be able to function, obviously. So also the distance. Most people are used to operating drones on Earth where you have a human running a remote control, and the human can react to whatever conditions that happen and guide the drone, hopefully safely. But you can't do real-time control of a helicopter on Mars, because it's right now the light time one way to Mars that is 17 minutes. So you couldn't have a human operator in the loop. And additionally, because we are actually doing it via the rover has its own operational cadence where it operates during the day, the Martian day, but you have to uplink all the commands in the morning, get the data to the afternoon. So we have this rover that's also our means of getting to the helicopter. What about energy? So the helicopter needs to be self-sufficient. Once it was deployed to the surface, it couldn't borrow power from the rover. One of the most common questions I would get is, well, does the rover act as an aircraft carrier? Meaning, does the helicopter come in and land on the rover and plug itself in to recharge? No, it does not do that. It has a solar panel on it, so it can charge. And once the rover deposited us, they wanted to stay safely away from us so that we wouldn't crash into them by accident. That would not be a good outcome. But because we do have, energy challenges, the helicopter just doesn't stay awake on the surface. waiting for us to talk to it. It spends most of its time sleeping so that it doesn't drain the energy, because all the processors and the electronics, when they're all powered up, they use enough power that it would drain the batteries completely empty within a few hours. And so we needed to be able to manage sleeping. So what's the first step in getting to Mars? Is that you have to design the helicopter itself to actually meet all these requirements. So we have to design it, then we have to build it, then we have to test it. Here is a picture from the surface of Mars after we were deployed. This is a picture from the Mastcam Z instrument on the rover, which can take really, at this point in the project, they could take really close-up images of the helicopter. And so I used this to point out the different features of the helicopter. So one thing you can't see, but is important, is that the total mass of the helicopter is around 1.8 kilograms, or about 4 pounds. So any one of you could easily lift the helicopter with one hand. It's very, very light. The blades themselves, if you can see my mouse, the blade themselves are constructed of very light but tough carbon fiber with a foam core. Each blade weighs about as much as a sheet of paper if you pulled it out of your printer. They're super light. People, when we hand it to them, they actually, their hands kind of fly up because they're expecting it to be heavy, but it's not. They're super light. And the legs and the spine, the shaft of the helicopter are all carbon fiber. So it's a very, very light system. And in order to meet the problem of the thin air, the rotor speed is about 2,500. It can go anywhere from 19 to 28, but based on what we found to be the density of the air at Mars, because it can actually vary depending on where you are, we're running at about 2,500 RPM. Typical Earth helicopters run on the order of 500 to 600 RPM because the dense air provides more lift, but we have to spin much more quickly. And we also, because we have to spin so fast and we have to control the helicopter at such a high rate, we actually put a Qualcomm Snapdragon processor as our main processor on the helicopter, which is a cell phone class processor, which is very powerful, much more powerful even than the rover's processor. So let's look at some of the other features that we had to figure out. We had to, you see the flat rectangular feature there, that's the solar panel. That's the panel itself was designed and tuned for the Mars spectrum, which is different than Earth's. And so this panel was built specifically for the light on Mars. We had to design our own telecommunication system. If you look very closely, you can see a little whip antenna sticking up from the center of that panel. We actually adapted a Zigbee radio system. Some of you may be familiar with that as a radio system that's popular for home automation. And so the same radio that's powering your sprinkler system is helping the helicopter to talk on Mars. So we designed a fuselage that has inside of it, we have the avionics processing itself, which includes the Snapdragon. We have a board with a second automotive microcontroller that does a lot of the flight functions. And of course, the software lives there. We have 2 cameras. One is a 13 megapixel color camera. One is a downward facing black and white, what we call our navigation camera, which takes pictures of features on the surface. We designed the fuselage to have this skin on it that would keep the heat in at night, but also absorb the heat during the day to keep us warm. And we used gas gap insulation. So it's basically an air gap. And then also around the batteries are what we call our survival heaters. These are heaters that keep the batteries warm at night. So part of if you want to look at the rover system itself, this is before deployment. This is how we actually flew to Mars and drove around on Mars looking for our landing field. Is the rover itself has really 2 major parts to the helicopter system. One is the helicopter itself. You can see it in its stowed position here where all the rotors are turned flat and it's pushed up against the bottom of the rover. That's the helicopter itself. And then we have what's called the helicopter base station itself. So that's actually an instrument payload on the rover that talks to the rover computer, but internally it has a radio that's used to talk to the helicopter. So the rover itself does not talk directly to the helicopter, it talks through the base station. So you can see how all this fits together in the pre-deployment as part of the project. So as far as the software design goes, we wrote software for 3 different computers. So there are actually 3 computers that are part of the helicopter system itself. So on the helicopter, as I mentioned before, we have a Qualcomm Snapdragon ARM processor. And for those of you who have owned Android phones in the past, it's from the Galaxy S5 era. So even though it's very powerful compared to the processor on the rover, even these days, the market is moving so fast, it's considered an old processor, but still, it's very, very powerful and has been performing extremely well for us. And so what things are on that particular processor is we have the telecommunications, which means the radio is connected to that processor, and the software that talks to the base station through the radio uses that. We have imaging. We have those 2 cameras that I mentioned, the color camera that points slightly below the horizon, and then a black and white camera that points down to the ground. There is also part of the guidance software that lives there that was designed by our guidance team that will take the imaging and use that to do feature tracking, where they see how features move from frame to frame. That's part of the way that the helicopter navigates, is by looking at the ground and seeing how features move, and it can infer from that what the speed and direction of the helicopter are. Power management, by this I mean that we have commands to turn on various hardware pieces of the helicopter as needed. So all that logic lives in that ARM processor. But in general, it does what we call data management as well. It stores all the telemetry that we gather on the helicopter and stores it for forwarding to the base station, for collecting into files that we can use as logs from the flights. And all that happens on that Qualcomm Snapdragon. So the Qualcomm processor is the one that boots up whenever the helicopter is powered on. The second processor that's on the helicopter is a Texas Instruments automotive microcontroller. It's a TMS-570. It's a Hercules controller. It's really designed for automotive use, so it's really tough. It's really robust. And so we do a lot of our main flight control on that processor because it's very robust. And it does the flight control. As I mentioned, the software is given waypoints, and it takes in data from sensors like inertial guidance unit and an altimeter. And along with that, it basically is able to control the trajectory that the helicopter is flying on. We also do motor control because obviously we're spinning rotors just to spin up the helicopter to give it lift and to translate it. And so we have rotor motors, and then we also have servos that control the pitch of the blades in order to give us lift and to steer us. And so there are software control loops that perform that function. And as I mentioned, we have sensors on there. We have a Bosch IMU, which is, again, very common in cell phones. When you lift your cell phone and it detects the rotation and the motion, it's a tiny little sensor that does that. And we have a laser rangefinder that points at the ground and bounces off the ground so that you can tell what your altitude is. And if anybody here is familiar with SparkFun, they were very excited because we bought our laser altimeter literally from their website. It's a do-it-yourself website that people like to buy electronic kits and build their own gadgets, and we bought one from them. So the helicopter itself has 2 processors, and then on the days that we fly, we power up the microcontroller in order to do flights. On the days that we don't fly, when we're just transferring data, we don't power it up to save the energy. So as I mentioned before, there's another part of the helicopter system, which is an instrument payload on the rover, and that's our helicopter base station. It uses the same exact Qualcomm ARM processor. As a matter of fact, it's the same exact avionics boards. They're just wired differently, and they're, if you want to think of it this way, they're mechanically arranged differently to fit within the box. Instead of a cube on the helicopter, they're meant to fit in an enclosure on the rover. And so the base station had two major functions. One was, while the helicopter was still attached to the rover, the base station would perform the charging function. So it had a charging circuit built in so that we could keep the batteries at a safe charging level. While we were attached to the rover, we kept it in a certain range where it wasn't low enough, where the batteries weren't damaged, but it wasn't high enough where if for some reason there was a short, obviously we wouldn't want the batteries to start to catch fire or start to vent where all, you know, chemicals go everywhere. So that would have been a very bad outcome, obviously, while we were still attached to the rover. So we never fully charged the batteries while we were attached to the rover. We always charged them to around 35%, which is above that, then the battery can start to get into some regions where if it gets shorted for some reason, a circuit failure or a wiring failure, then it could vent or catch on fire. But at 35% and below, even if there was a hard short on the battery, it would just discharge. So when we were on the cruise part of the mission from Earth to Mars, and on Mars itself, before we were deployed, we would always keep it in that sweet range so that the base station had the electronics and the software to perform that charging. And then once the helicopter was actually deployed to the surface, the base station has a radio that we turn on and we use it to talk to the helicopter, and we would we relay commands to it and we get data back. And so between all three of those computers, we wrote about 800,000 lines of code for the helicopter. So that was a team of 3 or 4 engineers at the peak. And we also had the guidance software people had another 2 or 3 people working on that part. So altogether, we produced the software during the development phase. It's based on a JPL open source flight software framework. It's called F Prime. It's actually been open. You can get to it on GitHub if you look at the URL that's in those slides. You can, or you just go to the public GitHub and you just type F Prime. You should be able to find the link. And this was an effort that JPL underwent about 3.5 years ago. We released F Prime to be open source so that we could do collaborations with universities, and plus people who want to do their own projects or even a flight project, if they're inclined, can go and get that software off of GitHub. Many of the components that are on that repo are ones we used on helicopter. And if you will, retire a helicopter, we'll be contributing some more back to that public repo. So if you go to that site, you can download it. You can actually compile it and cross-compile it for a Raspberry Pi, and you can run on a Raspberry Pi if you like. But we also have Linux and Mac versions that you could run on just a Linux machine if you like. So that talks about the software. So once we've actually designed it, how do you actually test it? Because we don't have Mars here, obviously, and we don't have a Martian atmosphere, and we don't have Mars gravity. So how do we actually test it? So that's step 2. JPL has a facility called the Solar Simulator. It's been used for the better part of 50 years to test spacecraft at Mars. It's about 70 feet high and about 25 feet wide. You can see a picture of it there. In the middle, you can see some of the engineers from the team setting up the helicopter early in testing. But that entire chamber can be closed, and then you can pump it down to whatever pressure you need for your project. In many cases, JPL spacecraft are put there and the chamber is pumped down to a vacuum. But in our case, we wanted to reproduce the atmosphere of Mars, so we pumped it down to 1%, but we also filled it with carbon dioxide, which is the dominant gas in the atmosphere of Mars. So we were able to actually reproduce the atmosphere of Mars in this chamber, and you can see because it's large, we were able to have room to do testing. In this particular picture, some of our early testing was done on a stand. You can see that triangular stand in that picture, and the helicopter is mounted on that stand because we had gradual testing. We didn't want to obviously just put it in there and try and fly right away because we built it up in stages. So we would put it on the stand and test that it was actually stable and producing thrust and so on. And then we would gradually get to the point where we fly. We also built a whole system. This was a science project in itself was we called it our gravity offloader. It was a tether system where there was a cable that came down from the ceiling and attached to the top of the helicopter at the solar panel. And this was an active control system. It just wasn't something like a spring, you know, a cable with a spring, but it would pull up as the helicopter flew to simulate the Martian gravity, because the helicopter is too heavy to fly on Earth. It can't actually fly on its own on Earth. It needs help. And so we had a whole computer system that somebody designed that would pull up on the helicopter as it was moving up and down to give a precise amount of pull vertically to simulate the Martian gravity. So that's really the way we reproduced the Martian environment. Was we built this chamber, we pumped it down, and we added this gravity offload mechanism to try to replicate the gravity of Mars. So how do you produce wind? This was kind of a fun project. We had some interns that helped out with this. And in the lower right, you can see what we called the fan wall. We actually took something on the order of 900 PC fans and mounted them on this panel. And somebody designed a computer system. We worked with some professors at Caltech on this, but somebody wrote software for a computer system that would ramp up all these fans together. So even at 1%, we could get enough wind to simulate upwards of 10 to 15 meters per second that you could see on the surface of Mars. So it's quite dramatic, because when we would do these tests, the whole thing would spin up and it'd do this giant roaring sound and rumbling from within the chamber, and then we could test the helicopter and see how it would respond to winds on the surface of Mars. So finally, we mentioned one of the challenges is the temperature on Mars. So this large chamber that I mentioned, the solar simulator, also has the ability to lower the temperature inside. So we would pump it down to Mars pressure, and then we would lower the temperature. These were very focused tests. We couldn't do this all the time because it was a lot of work and a lot of expense to do it. So we had a particular period of time of about a week where we would take this chamber, we would lower the temperature way down to those operating temperatures on the surface of Mars, and we would do our tests. We would spin the helicopter up and down. We would make sure all the systems worked. And because this chamber is so large, when we were actually running the chamber, we had to have 7 trucks a day come in to replenish the liquid nitrogen to keep it cold. So it was quite an involved test. But between all these various tests, we did extensive testing for the better part of 2 years in the chamber, and it really, really paid off. We were able to demonstrate that we could fly, demonstrate that we could control it, demonstrate that the software worked, and it was quite a beneficial time for us. And that's really how we were able to demonstrate that we could fly. So we did all this testing, and then we delivered the helicopter. We delivered it to the big building. I don't know if any of you have been to JPL and visited JPL, but there's a very big assembly building where they put all the spacecraft together. So as they were putting the rover together, we delivered the helicopter, and they integrated it with the rover. And we did a lot of testing there just to make sure all of the interfaces worked. And then we delivered it to the Cape, and then they launched it. And so now that we've done all of our testing, we designed it, we built it, we did all the testing, not only in the chamber, but also with the rover to make sure that it could talk with the rover just fine. Now we actually have to operate it. So that's step 3 in our process of operating a helicopter on Mars. So as I mentioned earlier, we had to actually plan how to do the operations because there isn't any direct communication with the helicopter. We had to do all of our interaction with the helicopter via the rover itself. So the rover has its own commanding system, its own ground tools, its own data processing tools. And so we had to do actual development on our own as a team to develop software tools to deliver our commands. We had to write our own software tools to take the format of the data that we would get from the rover and decode it back into the data that we were accustomed to seeing with the helicopter. So we spent a significant amount of time I would say essentially a year's worth of time planning and testing all of these tools and all these procedures. We had to write up procedures. We had to practice the procedures. So we had a number of cases where we would go to the Mars, what we call the Mars yard, where they have a test rover, and we would test our tools and test our commands with the substitute rover just to make sure everything worked together, and interacting with the rover teams. And so we had to do all this work as well. So here's a picture of us sitting in the control room at JPL, waiting for the data from the helicopter. So the rover itself has its own daily cycle. So the rover is not also constantly communicating with Earth. What happens is at the beginning of the Martian day, and so for those of you who aren't familiar, the Martian day is 24 hours and about 40 minutes long. And so relative to Earth's day, it basically walks by 40 minutes every day. And so early in the mission, the team was on what's called Mars time, where we would be, when the rover is actually doing its activities, the rover team is sleeping. And then in the afternoon, when the rover sends all its data back to Earth, the rover team on Earth wakes up, processes the data, and then gets ready for the next day. So the rover team itself is not in constant communication. As I mentioned, what they do is at the beginning of this Martian day, which they call a sol, they will uplink all the commands for the day, and then the helicopter or the rover basically turns off the radio and then does all of these activities asynchronously, meaning the people on the ground are not watching it. And then at the mid-afternoon of that Martian day, it turns on the radio and it relays the data, or the everything that happened. They relay the data of that back through an orbiting spacecraft, which has a much faster link back to Earth. And then the team on the ground actually processes the data. So as part of helicopter, when we were in the chamber, we were used to, in essence, real-time data. We ran our own ground system. We would get instantaneous data back from the helicopter, and we could evaluate the data and then immediately turn around and run another test. But we had to go through and do a process by which we designed these procedures and tools to actually interact with the rover's tools when they would return our data from us, and we would submit our own sets of commands in time for them to uplink it at the beginning of the Martian day. And so all the commands on the helicopter, and in a similar fashion on the rover, the patterns are very similar, is that we would write a list of commands to execute on the helicopter or the base station. One of the engineers would write it in just a human readable form. And then we would take those commands and we would compile them into a very tiny binary file. And we call those sequences. So those are sequence files, if any of you have done any kind of spacecraft operations before. So we have command sequences, where in essence a list of commands that are compiled into a binary and sent to the helicopter to be executed. And so on the rover side, I would write the sequences for the rover, which would end up taking the helicopter sequences and transferring them to the base station and telling it to start executing them. And so during a flight, we had as many as 10 of these things running in parallel, because the sequences run on what are called sequence engines. You can almost think of them like a little program running on a processor, but there's software modules that can take a binary sequence and start executing the commands. And the base station and the helicopter both had 4 of these sequence engines each, and so we were able to run multiple sequences at the same time to get the helicopter to do what was needed. And so that was really our daily cycle during the helicopter, is that we would write or update sequences to run on the base station and the helicopter, and then we would give them to the rover team, and then they would execute them for us on the rover. And that's how we would interact with the helicopter and get the data back. So looking at the helicopter itself, what kinds of data are produced by the helicopter? We have 1 second real-time telemetry. So the helicopter is producing engineering telemetry at a rate of once a second, and then the helicopter basically bundles that all up and sends it on the radio to the base station. So the base station receives the data and stages it in the memory of the base station. And then the rover will periodically poll the base station, will periodically query the base station and say, give me the latest values that you have stored in the memory. And then it'll bundle that data into its own data format and then send it back to the ground in the afternoon so we can decode it. So interacting with the helicopter, the base station, is a series of, we send it the sequences, we tell it to execute these sequences, and then we poll it to see what data it's producing. And that poll data is then stored for later digestion by the helicopter team on the ground. We also produce files. So the helicopter, when it's flying, the guidance algorithms run at about 500 hertz, 500 times a second. It's very, very fast. And we generate quite a bit of data during each 500 hertz cycle. And that data is essentially stored in RAM during the flight. And then once the flight is done, all those RAM logs get basically pushed into a file or written to a file. And then we can actually transfer those files through the rover back to the ground and then decode those logs and get very detailed information about what happened during the flight. The other files that are generated are those color and black and white images, those cameras that I mentioned. The images are actually used by the guidance algorithms to, as I mentioned, to compute position and direction or orientation. But we can also by command grab those images as they're going by, because most of those images, they run at 30 times a second. Most of those images are just used by the software and discarded, but you can actually, in the software, grab those images and store a few of them for transfer to the ground. And you can see that black and white picture in the lower right-hand corner was the very first picture that we downlinked and was the one that went out to the world. It was a picture pointing at the ground where you can see the shadow of the helicopter on the ground during that first flight. So that was quite the epic first picture. And as you see above that, there's a little plot of some of that high rate data that we looked at. And so that's really how we get the data. So we get the data in the form of these binary files from the rover. So we had to write tools to decode that data back into the original channels that the helicopter had. And we had a whole development effort where we used Elasticsearch. Some of you may be familiar with that technology. It's a database technology, and we would decode all of our values and then store them in Elasticsearch. So we had Python tools that we wrote that would decode these files and put them into Elasticsearch. And that allowed us to do all kinds of querying of the data to figure out what happened. We can plot the data. You can see that one plot above just by getting the data back. So we had to do all of that. So once we're there, then we have to do the final step, which is the actual execution. So this is where all the fun pictures come in that everybody likes to see. So the actual execution of the flight, the first interesting step in that, we had, as I mentioned, cruise and surface charging. But the first thing we had to do was the actual deployment of the helicopter. It was attached to the bottom of the rover in a folded configuration. So we had, over the space of about a week, we had to go through a series of these very critical and non-reversible pyrotechnic firings. We actually explosive bolts firing to release various parts of the helicopter. We also had motor actuations where we had motors rotating the helicopter into place. And so we were very intensely interacting with the rover team to issue the right commands to do all these steps, and then to do inspections of all the various steps, because each day we had to verify via pictures. The Watson camera on the rover on the end of the arm basically would rotate and look under its own belly so that we could see these pictures of the deployment happening. And then we had our final drop to the surface. So you can see these various deployment stages here, a little animation. There's the cover that protected it, and you can see it rotating into places. The legs were held in place against the body until they could fire these explosive bolts and finally make the helicopter so that it was ready to drop. And then we had a very tense, very critical time where I mentioned before that they typically do rover operations where they start at the beginning of the day by sending commands, and at the end of the day they get the data. Well, we had a very rare live radio link where we would watch it to make sure that it dropped successfully on the ground, and then we could drive off of it and expose the solar panels to keep the battery where it needed to be. So right after we dropped, though, we took a picture in lower right-hand corner from the color camera as we're hiding underneath the rover. So that was a pretty cool picture. So deployment, we had to get the helicopter ready for flight. The blades were restrained while we were attached to the rover so they wouldn't clatter against the body of the rover and damage the blades. So we had to do a special software that function. We had a special state machine to just pop them because you can see they go very quick. They both go clockwise if you're looking down to pop out of the restraints, because normally they counter rotate for flights, but we had to run the software in a special mode to release them. And then we did a series of checks where we did a relatively slow 50 RPM spin. You can see that in the lower right-hand corner, just to make sure all the motors were actuating correctly. And then our last checkout activity was going to be a high-speed spin where we spun up to the full RPMs and back down again, because we wanted to make sure that the guidance sensors were reacting, the inertial guidance unit was performing correctly and everything. So that's when we had our first anomaly. That was, some of you who are following the rover, the high-speed spin didn't work. We discovered that there was a bug in our hardware, believe it or not. So a lot of the hardware logic is encoded in what are called field programmable gate arrays, or FPGAs. So it's custom logic that JPL designed. And there's a watchdog feature in the hardware that if the processor were to go off in the weeds and stop functioning, then the hardware would prevent it from executing flights. And we discovered that the watchdog logic in the hardware had a bug where it was not correctly detecting the values sent from the software. And so it would prevent this transition to the power mode, which allowed us to do a flight. So we had a period of 4 or 5 days where I was working very intensely with the hardware designers to try and figure out a workaround. And we figured out one where we can actually use some special software test commands to send transactions directly to the FPGA and reset that watchdog logic. And it just so happened that when the reset was exiting, the timing was such that now the watchdog function on the hardware actually works about 85% of the time. That's what we determined by doing experiments on the ground and actually experiments on the helicopter itself on Mars, where we would send these transactions and see how often they would succeed. And so once we figured out that workaround, we were able to repeat the high-speed tests and perform all of our flights. We did 5 flights. One of the flights actually had this issue manifest, so we had to rerun it, but the second time it ran just fine. We actually do have a software update to work around this hardware problem, but we have not installed it yet because we wanted to get through our prime, if you will, our prime mission of doing the flights, because the process of installing the software would probably cause a delay of about a week, in order to get it all the way to the helicopter, update the software, and then do some basic testing. And so the software update is still pending because this workaround that we found works almost all the time. So that was the big anomaly that we had to work our way around. So once we did that, we were able to execute our flights. And so this is kind of a quick overview of the flights. So flight 1, we rose vertically and hovered at 3 meters. That was really to prove that we could actually even fly, because again, even though we tested it in the chamber, we didn't know for certain that we would fly. Here's a video. I'm not sure that it will necessarily show well over Zoom, but you can see the helicopter taking off and landing. And again, we have that. These are from the Mastcam Z instrument on the rover, and you can see the black and white that we took. So flight 2, we wanted to test that we could go higher and that we could actually do a basic translation, which means we would basically move horizontally. So we rose to 5 meters and we did a 3-meter translation. And that proved that we could actually move horizontally. It's actually a big deal because hover is, if you want to think of it as sort of a static attitude, but different dynamics come into play when you translate. So we want to prove that that was feasible. And this is where we got the first color image in the lower left right-hand corner right here. And then this is a view, this is a video of that second flight where you can go play here. You can see in this one with the second flight, it's actually moving, the directional translation is away from the rover. You can see that it's pivoting, it's rotating because we wanted to get a couple different pictures. So that was the second flight. So the third flight, this was the one that was, let me see. I'm trying to get it to go to the next slide, but it doesn't want to. There we go. Flight 3 was to fly 50 meters to the north and then return. So this was a much more ambitious translation. It would allow us to test longer flights. And one of the cool things that came out of this was we got on the color camera, we were very fortunate. We got a picture of the rover. You can see the picture in this is a zoomed in. You can get the full size picture on the website, but this is zoomed in. You can see the rover peeking out from the corner. And what's really cool is you can see if you will, the blast zone from the landing of the rover right here, where it scoured the surface. And then you can see all the tracks around where they deposited the helicopter for the helicopter flight. So that was a very exciting flight. And they actually just released in the last 24 hours, if you have 3D glasses, the red-blue glasses, there's actually a 3D movie of this flight. But you can see in this one, you can see the helicopter take off, and then you can see it disappear off the picture to the right. So this was a very exciting flight for us because it went so far. And came back safely. So I'll pause this because I know I'm running short on time. So let me move on. So flight 4, once we did the first 3 flights and we saw that we could fly long distances, we got much more daring. And we started to see, well, let's use this actually to scout another location for the helicopter. So we flew 130 meters to the south and then we returned back. So that's 260 meters total. That was a very long distance. And on the way, we took very detailed black and white images to scout the landing site. This middle picture you can see here is basically taking those nav images and flattening them so that you can see what the surface looked like after we flew over it, because the camera itself is fisheye. We took some, in the upper right-hand corner are the color pictures. We took 5 color pictures as we flew. And then they were able to take those pictures in the lower right, and this is an overhead view of a map of the area, and they were able to take the color pictures and superimpose them on the map so you can see the detailed color images that the helicopter took as it flew. And this is a video of, oh, this one actually does have audio to it. Can anybody hear the audio? If I'm not sharing audio, what's very interesting about this video is that they were able to point a microphone at the helicopter and actually get audio of the helicopter as it was flying, which is pretty amazing when you consider that the helicopter was about 60 meters away and the Martian atmosphere is so thin. So you can see it heading to the left of the picture, which is south. And again, because we're running short on time, I won't show the whole video, but all these videos are available on the website. These are actually internal ones, but I was able to release them and show them to you. So finally, Flight 5 was the one we did about a week and a half ago. We were able to relocate to that new location that we scouted out on the previous flight. So we went 130 meters to the south to an area that was near the end of the fourth flight. We found a nice smooth area that was free of obstacles, and we were able to land there. On the right is an animation put together by combining the black and white pictures as the helicopter was coming in for a landing on its landing spot. And then the left-hand picture was a picture taken by the rover as it flew the navigation cameras. It's a very nice picture because it shows the helicopter against the background of the delta to the west of the landing site. And so at the time that I was writing these slides, they're still working on getting imagery down from the rover and the helicopter, which has since been released. You can look at it on the website. But since I had to get these slides through the release process, this is what I could release at the time. So these were all the flights. These are the ones we did on our prime mission, if you will. And so the question is, what's next? Because the helicopter is doing so well and taking very nifty pictures, they've extended our mission for at least a couple of months. And what we're going to do is, the first part was just to prove that we could fly. And so the second part is to do this operations demo, where we take the helicopter and we fly it places and try to have it act as a scout. The rover doesn't need our data, but they'll be happy to look at it. But this is an idea that we can fly every couple of weeks, do these scouting flights, and then that will inform future helicopter scouts about how they can do this kind of scouting if they want to scout ahead for a rover or for maybe future astronauts. So we're doing a series of flights where we'll go and we'll scout out a landing location for the helicopter itself and then go there. And these will be much more risky because we'll go longer distance over much more varied terrain. So stay tuned. There is a URL there at the bottom for people who want to go and look at more cool pictures or read some of our blog entries about the helicopter. So that's the end of my slides. I think I'm at the end of my time, but Abhishek, if we have time, if people want to ask a few questions, that's your call.
Yes, so thank you very much, Tim, for an excellent talk. If people have questions, so we are in a break till 2:30, so we can actually ask questions. If somebody wants to take a break, go ahead. But please, we are here. If you have questions to Tim, please unmute yourself and you should be able to ask questions.
Hi, this is Sharon Hu. Can you hear me?
Yes, Sharon, we can hear you.
Okay, I don't know if I'm supposed to turn on my camera or not.
You can turn on, Sharon, if there's a problem.
Yeah, but says enable. That's okay, don't worry about it. That was a very interesting, very exciting talk. I really enjoyed it. One question I have is the Mars, in terms of radiation, is that how does that compare to the radiation or these high energy particle levels there versus on the Earth? Is that a concern or not?
Yeah, it was a concern. And because a lot of our hardware is not radiation tolerant, it's not designed to be tolerant to radiation hits. A lot of it's just off the shelf commercial hardware. And so we honestly didn't know how well it would do. We did some testing here where we radiated our parts and it actually did pretty well. And that gave us comfort that when we got there that it would perform fine. And so far, all through, the more dangerous time is during cruise when we're out in space and we don't have any shelter from the atmosphere or from the planet of Mars itself. But it performed perfectly during that time. And since it's been on the surface of Mars, nothing bad has happened. The parts have all performed just fine. We haven't seen any evidence. We saw one, the only thing we saw one, I mentioned earlier, we take those data logs. We actually saw one bit flip in one of those files. So it must have been flipped in memory as we were copying it. But other than that, we have seen no evidence at all that we've had any radiation effects.
And do you think that's just because these hardware are good enough in terms of their resilience to radiation, or it's just kind of luck?
I would say it's probably both. I mean, if you think of lots of times hardware is like, you can think of like shooting a gun at a target. The smaller the target, the less likely you are to hit it. And so our hardware is very miniaturized and it operates at lower consumer voltages. So there's not a lot of energy to liberate if there is an upset event. And so the hardware by itself is actually pretty robust. And then also, you know, we're not on for that long, and we're small, and so there's probably an element of luck that we didn't get hit by anything. So we're just saying, hey, that's great, we didn't get hit by anything. That's kind of our mitigation strategy.
Is there a reference or something that we can point to if we say, you know, on Mars, here's the level of radiation that we should be prepared for?
I will freely admit that's not my area of expertise. There's been lots of publications and papers which you could probably find on the radiation environment at Mars, because there's been enough missions there that they've characterized it pretty well.
Great. Okay. Thanks a lot.
So I would encourage you to look for those. I'm probably not the guy to go ask about it.
Thank you.
You're welcome.
Any other questions?
Yes, this is Albert Chang from the University of Houston. So my question is also following up from Sharon's question on the radiation. So besides the hardening on the microprocessors, so there are no additional fault tolerance mechanism, hardware and software on the helicopter?
We do have an FPGA that FPGA that I mentioned. It is a rad hard design, so it acts as sort of the core of the system. And we have these watchdogs, and so it's if you will the most reliable part of it that we have. And so, but our mitigation, we don't really have any mitigation. Our fault response is if something looks weird, we try to land, do our best to land. But we are a technology demonstration, so we didn't put a huge amount of engineering into fault responses, just because we were putting all of our energy into figuring out if we could fly or not. So there isn't a comprehensive mitigation strategy if we do actually have an upset.
Thank you, Tim. Yeah, thank you.
We have probably time for one more question.
Okay. Hi, team. Thanks a lot for the talk. I have a question. You mentioned that there in total about 800,000 lines of code, software code. So did you guys do any, I don't know, validation, verification of those code? What types of approaches did you try?
We did, so in the F prime software framework, I guess there's two levels of testing that we did. Let me make that three. Okay, so each in the F prime software architecture, the software is decomposed into components, and so part of the code generation that we do for components is they generate test components that you can connect to the components under test and write a whole bunch of unit tests. So we did extensive unit testing at the component level of each of the modules. For the GNC code, the guidance, navigation, and control software, they had their own simulation environment where the same code that ran on the helicopter could be compiled against the simulation environment and tested there. So they did extensive not only code level testing, but also dynamics level testing in their own simulation environment. And that's been hugely productive for them to prove out these flights without actually physically flying. And then, of course, we had at the system level, we had all the testing we did for 2 or 3 years of actually flying the helicopter in the chamber to bring out issues that we saw there. So I guess you could call that the level of verification that we did, was at that module level, and then simulation, and then actual flight testing in the chamber. And so far, we've only discovered one actual software bug. It's like a scaling factor in one of the sensors that made one of the hardware devices appear warmer than it is. But that's the only bug we've really found in the software since we've been operating on the surface of Mars. It's actually done really well in that regard.
Thank you. And if I may, a very quick question. So the anomaly you observed during the high-speed spin test, do you think is that caused by something unique on Mars, or this is just somehow it happened?
So I don't think let me put it this way: it's unique, but it's not because we're on Mars. It's because of this particular. Our best theory is that because we didn't see this problem extensively on Earth, it popped up from time to time, but But in all honesty, it was a blind spot in our testing. We thought it was an idiosyncrasy. And so we sort of ignored it, but then it bit us. But the nature of the nature of the bug is that it depends on how long it takes that flight computer, that second processor, to boot up that microcontroller. So it's a timing related issue.
I see. Interesting.
And so the unit that we had on Earth had different timing. So we think that the clocks, if you want to put it, the instances of the clocks on the two units were just different enough that they were on the hairy edge such that it works on our units on the ground here in the lab, but it didn't work on the version that was on Mars. So it wasn't specific to the Martian environment, unless maybe the running slightly colder would influence the clock somewhat. But it's more, the instance of the clock that's on Mars may be causing it to boot with slightly different timing and tripping this particular bug.
Very interesting. Thank you.
You're welcome.
Thank you very much, Tim. This has been a great talk. I'm sure everybody has lots and lots more questions. But I think maybe they can email you or reach out publicly if they have more questions. So thank you again for your time, and thank you for the great work.
You're quite welcome.
What's next?
Great ride, and it's great to share it with everybody.
Thank you.
Thank you, Tim.
Take care, everyone.
All right. Well, at this point, we do have one break until 2:30, and then we will start with the second technical question that includes